Our subject is VLSI design and subject code is 19ECY01. We are going to see the unit 1. It is introduction to mass transistor. First of all, we'll see what is VLSI stands for. VLSI stands for Very Large Scale Integration. This is a field which involves a packing more and more logic devices into smaller and smaller areas. VLSI circuits are everywhere. Whatever we are using in our day-to-day life, VLSI circuits are involved in that. That is your computer, your car, your brand new state-of-art digital camera, the cell phones which are using, and your day-to-day appliances which are involved in our day-to-day use. What are the levels of ICs? ICs are of four levels. That is a small scale integration, medium scale integration, large scale integration, and very large scale integration. Small scale integration in the sense it consists of tens of transistors. Medium scale integration in the sense it consists of hundreds of transistors. Large scale integration in the sense it consists of thousands of transistors, which is demanded automation of design process. There is the CAD started evolving with this large scale integration, and very large scale integration in the sense it consists of tens of thousands of transistors. The metrics which we can use for achieving the VLSI design is it has higher speed, lower power, physically smaller, it has integration reduces manufacturing cost, higher reliability, and more functionality. The VLSI backend and frontend. Whatever the VLSI backend, VLSI backend includes routing, place, and floor planning. Backend includes the development and fabrication part. There is a fabrication of the layout. It takes place in the VLSI backend process. It is too costly and time consuming process. Physically designing and layout refers to the backend process, which the backend design engineers can do that. VLSI frontend in the sense it includes the designing and testing part. It uses Verilog and HDL, that is VHDL also. RTL designing, minimizing delay, and simulation, it refers to the front end process. These are all the VLSI back end and front end process. Next, we'll see what is the difference between the BJT and FET. BJT, in the sense, it is called as a bipolar junction transistor. It is called as a bipolar device. FET is a field effect transistor, which is called as a unijunction transistor. And a BJT, its operation depends on both the majority carriers and minority charge carriers. But in fact, its operation depends on majority charge carriers, which may be holes or electrons. In BJT, the input impedance of BJT is very less. That is, it ranges between 1K to 3K. The input impedance of FET is very large. The BJT is a current control device. The FET is a voltage control device. The BJT is cheaper. The FET is very costly when compared to the BJT. BJT is bigger in size than FET. FET is smaller in size than BJT. BJT has three parts, that is a base, emitter, and collector. FET has three parts, that is drain, source, and gate. BJT consumes more power, FET consumes less power. BJT has negative temperature coefficient and FET has positive temperature coefficient. These are the difference between the BJTs and FET. Because of the advantages which the FET has, we are preferring most in our day-to-day uses. Next one is a MOS transistor. First of all, we'll see what is a MOS and why we are using the MOS transistor. MOS transistor is a majority carrier device in which the current in a conducting channel between the source and drain is controlled by the voltage applied to the gate. That is, the voltage is controlled by this device. The NMOS transistor has a majority carriers of electrons, and in the PMOS transistor, the majority carriers of holes. Either the majority carriers may be the electrons or the holes according to the type of transistor we are using. And here is a symbolic representation for the MOS transistor for the N channel and P channel transistors. And here are the modes of operation. There are three modes of operation in which the MOS regions can operate. First one is the accumulation mode, next one is a depletion mode, and third is an inversion mode. The accumulation mode, it consists of the structure which has a p-type body, and in between the silicon dioxide insulator layer it separates a p-type body and polysilicon gate. The polysilicon gate consists of the electrons and p-type body consists of positively charged holes. So the voltage is Vg, that is a gate voltage. The gate voltage controls all of the modes. According to the gate voltage, the modes differs related to the accumulation mode, depletion mode, and the inversion mode. When Vg is less than 0, what happens is in the p-type body the holes gets accumulated, and then in the polysilicon gates the electron gets accumulated. But when Vg, it varies between, that is a gate voltage, when it varies between 0 to your threshold voltage, it is called as a threshold depletion mode. And in the depletion mode, what happens in the sense, that is the holes which happens in the p-type body, it depletes into the polysilicon gate, so that it is called as a depletion mode. And in the inversion mode, what is the condition in the sense, when the Vg is greater than Vt, that is your gate voltage should be greater than the threshold voltage. At this time, what happens is the depletion region, this the holes which reach your polysilicon gate and the electrons which carries over the polysilicon gate, it is pushed to the depletion region, so that the mode is inverted, that is holes get passed to the polysilicon gate and the electron gets passed to the depletion region, so that it is called as an inversion mode. So all these three conditions are very much important for the modes of operation. That is, for the accumulation mode, your gate voltage should be less than 0, and in the depletion mode, the gate voltage should be between 0 to your threshold voltage, and in the inversion mode, your gate voltage should be greater than your threshold voltage, so that the regions are inverted with the holes and electrons. Next one is the regions of operation of your MOS transistor. The regions of operation, what happens in the sense, there are three kinds of region, which is your cutoff region, non-saturation region, and saturation region. In the cutoff region, what happens is, that is in the p-type body, it has two n wells. So the gate and the source, which is connected together with the help of an voltage which is called as VGS, and gate and drain is connected to the together with the help of an voltage source which is called as gate to drain voltage. So when this VGS it is equal to 0 and VGD it has no source, it is called as a cutoff region, because no channel is formed between this. Here there is no channel is formed, so there is no current flow between your drain to source which is equal to 0. This is called as a cutoff region. And when that condition is VGS is greater than VT, that is gate to source voltage is greater than VT, and gate to drain voltage it is equal to the gate to source voltage, there is a channel which is formed between both of the n wells with a negatively charged particle. So that in this region what happens is drain to source current increases with VDS, which is called as the non-saturation region. And in the saturation region, what happens is the gate to source voltage is greater than VT and gate to drain voltage is less than VT, less than the threshold voltage. So the channel which is formed in between the N wells is pinched off. And so in this case, your drain to source current is independent of the drain to source voltage. These are all the three regions of the operation, which is your cutoff region, non-saturation region, and saturation region, which works upon the condition through gate to source voltage. This is a PMOS transistor. Instead of the NMOS transistor, if we are using the PMOS transistor, the body here is a N type and the well here which is used is a P type well. Along with the source to gate is connected together and drain to gate is also connected together with the help of an voltage source. The three region is very much common compared to the N region. The PMOS also can use the same three region. Next one is a CMOS logic, which we are using CMOS in the sense complementary metal oxide semiconductor logic. So what is meant by the CMOS inverter? Inverter in the sense whatever input we are giving, it gives an opponent output. That is called as an inverter, which we use with a triangle shape and bubble symbol, which we use in the normal digital circuit. But here, what we are using a PMOS transistor and NMOS transistor. The gate of the PMOS and NMOS transistor is connected together to form an input, and the output is taken from the other end. The PMOS transistor is connected to the VDD and NMOS transistor is connected to the ground. So this is called as your inverter, which is called as a CMOS inverter. When a PMOS transistor and NMOS transistor is connected together, it is called as a complementary metal oxide semiconductor. So we can see an example for the NAND gate truth table and the NOT gate truth table. For NAND, what we are using is your PMOS are connected in series parallel, and your NMOS transistors are connected in series. For the two input, only two transistors are used for the PMOS and the next topic is CMOS logic. CMOS, in the sense, it is complementary metal oxide semiconductor logic. In this, we are seeing the inverter. What is an inverter? In the sense, whatever input we are giving, it complements the output. If the input is 0, the output is 1. If the input is 1, the output is 0. So the CMOS inverter, in the sense, combining both the PMOS and NMOS transistor, is called as a CMOS inverter. So PMOS is connected to the VDD and NMOS is connected to the ground. In this, both are connected together to a single input A and both are connected together to a single output Y. So when an input is given, it will be inverted at the output part. So we can see the examples for the CMOS as CMOS NAND gate and CMOS NOR gate. CMOS NAND gate, in the sense, that is two PMOS transistors are connected together in parallel and two NMOS transistors are connected together in series. When there is a two transistors are connected together. When there are three inputs, three transistors are connected together. So PMOS is connected in parallel and NMOS is connected in series, which is called as a NAND gate. For NOR gate, PMOS will be connected in series and the NMOS will be connected in the parallel. For two input, two transistors are used, and for three input, three transistors are used. So this is the difference between the NAND gate and NOR gate of the CMOS circuit. So when we give the two, when we take an example for a two input, that is A and B. For 0, 0, the pull down network will be in off condition. Pull down network, in the sense, NMOS is called as a pull down network and PMOS is called as a pull up network. So pull down network will be in the off condition and pull up network will be in the on condition. So when this is in the on condition, we'll get the output as 1. When the input is changed to 0 and B is 1, pull down network will be in the off condition and pull up network will be in the on condition, for which the output will be, output Y will be 1. And for 1, 0, pull down network will be in off condition, pull up network will be in the on condition, for which the output is 1. When the both of the inputs are 1, 1, what happens in the sense, pull down will be in the on condition and pull up will be in the off condition. So when pull down network is in the on condition, the output is almost 0 because the grounded will be a 0 output. So this is how your PMOS and NMOS transistor works with respect to the input what we are giving. So this is the general structure of your CMOS structure. The top network consists of the PMOS, which is called as a pull-up network, and bottom network consists of the NMOS, which is called as a pull-down network. The pull-up network and pull-down network are connected together for one input. The output is also taken from the same. This is a general logic gate using the pull-up and pull-down networks. This is a CMOS NOR gate. So CMOS NOR gate, as I told you already, the PMOS transistors are connected in series and NMOS transistors are connected in parallel to each other. If we are using the two inputs, we are using two transistors, and if we are using the three inputs, we are using the three transistors for PMOS and three transistors for the NMOS. When it is 0, 0 as an input, what happens in the sense, the output will be 1. So this pull up network will be in the on condition and pull down network will be in the off condition. So the output for this 0, 0 is 1. When the input is changed to 0, 1, the pull up network will be in the off condition and pull down network will be in the on condition. Because if the pull down network is in the on condition, the output is 0. When the input is changed to 1, 0, the same criteria repeats here. Pull down network will be in the of on condition, so the output is 0. When both of the input is 1, 1, the same conditions happens here, so the output is 0 here because the pull down network will be in the on condition. And this is the structure of the compound gate. So the compound gate, in the sense, A dot B plus C dot D, the whole bar is called as the compound gates, which is A, B is a input and C and D are the outputs here. Next one is a pass transistor. Pass transistor, in the sense, why we are moving to the transmission gate, what is the advantage and disadvantages of the pass transistor, we'll see here. That is, for NMOS, what happens is when your gate is 0, the switch is in the open condition. That is, a connectivity between the source and drain will be in the open condition. When G it is equal to 1, the connectivity between your source and drain will be in the closed condition. So we can take an example with G is equal to 1 in the sense, for for G is equal to 1. For 0, we are getting the strong 0 output because there is a closed loop. And for 1, what we are getting is we are getting a degraded one. For PMOS circuit, what is G? When G it is equal to 0, there is a closed loop between the source to drain, and when G it is equal to 1, there is an open loop between the source to drain. So when G is equal to 0, we are comparing with both the 0 and 1. We are getting degraded 0 as an output and strong 1 as the output. So in NMOS, we are getting strong 0, and in PMOS, we are getting strong 1. So this is the thing which happens in the pass transistor, which we see separately your NMOS and PMOS transistor with strong and degraded outputs. Next is the transmission gate, which we are seeing together with the both of an NMOS and the PMOS. So this is a transmission gate diagram which we are using symbolic representation. When gate is 0 and GB it is equal to 1, the loop is open, and when gate is 1 and when GB it is equal to 0, the loop is closed. So it passes strong 0 and it passes strong 1. But when we compare in the NMOS and PMOS transistor, in NMOS it passes only the 0 strongly, and in PMOS it passes only the 1 strongly. So when we are combining the NMOS and PMOS together, which is called as a transmission gate, it passes strong 0 and strong 1. Because of this criteria only, we are combining these two, that is a PMOS transistor and NMOS transistor, which is together, which is called as a transmission gate. Next one. Sorry, which we see is a tri-state circuit. Tri-state circuit in the sense we are giving the three inputs, that is A, enable, enable bar, and Y as an output. When A is 0 and enable bar is 1, your impedance will be your output. And when A is 1, with enable 0 and enable bar as 1, impedance will be your output. But when same with respect to 0 and 1, when you are giving enable as 1 and enable bar as 0, you will be getting as such what input you are giving, you will be getting as an output, that is 0 and 1 you will be getting continuously. This is a pictorial representation of your tri-state inverter. And next, when we are using the multiplexer, what happens in the sense we are giving the two inputs, that is D0 and D1. When the selection lines are yes and s bar, we are using them as a selection lines. So when D1 is given as x and D0 is given as 0 1, it comes to the output whenever your selection line s bar is 1. So when D1 is 0 and 1, whenever this yes is 1, you will be getting direct input of the D1 to your output with respect to that of your yes, that is a selection lines. This is a multiplexer using the transmission gate in which the inputs are D0 and D1. So with respect to this inputs and the selection lines, you'll be getting the output. If D0 is 0 and 1, if S bar selection line is 1, you'll be getting D0 as output. If yes selection line is 1 is set to 1, whatever the input you're giving as D1, you're getting the output as 0 and 1. The next topic what we are going to see is a long channel IV characteristics, that is a current voltage characteristics. What is a MOS transistor? It is modeled as a voltage control switch. The NMOS transistor's current equation is given here. Charges included in this channel, it depends upon the gate to source voltage, that is VGS, which is called as a gate to source voltage. IDS is in the sense that is drain to source current, which is a charge induced in the channel divided by electron transit time tau. What is the transit time? That is the length of the channel L divided by the velocity V. Tau it is equal to L divided by V. Tau is a transit time. V, the voltage is given, it is equal to mu into EDS. What is mu? It is electron of the hole mobility, and EDS is a electric field which is drain to source. EDS is also given with an equation. It is called as VDS divided by L. VDS divided by L is called as your EDS. V it is equal to mu into EDS. So for EDS, we have given the formula VDS divided by L, which is called as mu into VDS divided by L. Next is your transit time. Transit time is given with an equation L divided by V. So L divided by V already we have given with a equation mu into VDS divided by L. We can substitute in here. When this L goes to the numerator, it is L square divided by mu into VDS. So finally, tau it is equal to L square divided by mu into VDS. The next one is we'll see the three region: cutoff region, saturation region, and non-saturation region. So in the cutoff, or it is also called as a subthreshold region. So the equation for this is, that is a condition for this is VGS, that is your gate to source voltage should be less than your threshold voltage. IDS it is equal to 0, that is your drain to source current equal to 0. Am I clear? There is two condition which you have to follow is gate to source voltage should be less than the threshold voltage and drain to source current should be 0. In this, the transistor will be in the off condition. Channel is not formed here. So there is no conduction between the drain and source. When there is no conduction between the drain and source, there will be no current between the drain and source, which is equal to 0. That is what here we have mentioned, ID is equal to 0. Next one is a non-saturation region. Non-saturation region in the sense, here we have to follow the condition Vg it is equal to VGS minus VT. VT it is nothing but your threshold voltage, and induced charge it is equal to QZ, where QZ can be given as Eg epsilon I epsilon naught W into L. Eg we know already, it is average electrical field, and epsilon I it is called as a relative permittivity of insulation between gate and channel, and epsilon naught is permittivity of the free space, which is 8.854 into 10 cups minus 14 Fermi per centimeter. W is the width of the channel. Eg can be written as VGS minus VT minus VDS divided by 2 divided by T naught X. So what is T naught X? It is called as the oxide thickness. Also we can write an equation for this induced channel QZ, which is equal to Eg into this epsilon I epsilon naught into WL. So this Eg can be written and it can be replaced with this equation VGS minus VT minus VDS divided by 2 by T naught X into epsilon I epsilon naught divide W into L. So we can replace with IDS, it is equal to QC divided by tau. So what we can write is QC, already we have found out the equation here. Just substitute this equation for the QC criteria here. We can substitute the same equation here. Finally, when K it is equal to epsilon I epsilon naught mu divided by T naught X, this equation can be rewritten as VGS minus VT minus VDS divided by 2 into KW divided by L into VDS. So this can be rewritten as this VDS can be multiplied with the interior part, which we can write as VGS minus VT into VDS minus VDS square divided by 2 into K into W divided by L. This is for the non-saturation region for the condition when VGS is less than VGS minus VT and beta it is equal to K into W divided by L. This can be rewritten as this K into W divided by L can be written as beta into this term can be written as usual. So for the gate capacitance, it can be written as Cg. It is equal to epsilon I epsilon naught WL divided by T naught X. So it can be replaced as Cg divided by L square into mu. Cg also can be written as C naught W into L. W you know with L is a length and C naught is a gate capacitance per unit area. For IDS, it is equal to VGS minus VT into VDS minus VDS square divided by 2, and for those it can be written as C naught W divided by L into mu. And for the saturation region, for the last one, what is the condition is? The condition VDS it is equal to VGS minus VT. The current equation between the source and drain can be written here. IDS it is equal to VGS minus VT into VDS minus VDS square divided by 2 into KW divided by L. So for this VDS we can substitute this VGS minus VT and it can be multiplied together. So VGS minus VT into VGS minus VT can be written as VGS minus VT the whole square minus VGS minus VT the square. It can be written as usual. So the LCM can be be taken here into W divided by L. So this can be replaced divided by beta divided by 2, which can be written as E naught W divided by L into mu. So this is a graphical representation with respect to the drain characteristics. So it is drawn between your drain source voltage VDS in volts and the drain current ID in milliamps. So the depletion mode and enhancement mode is given here. During the depletion mode, the graph of gate to source voltage, it decreases with the negative criteria, that is of 0, -1 volts, -2 volts, -3 volts. Under the enhancement mode, it increases with the positive criteria. This is the IV characteristics of the graphical representation which we have shown here. Next, we'll see what is CV characteristics. CV, in the sense, it is called as a capacitance and voltage characteristics. Each terminal of a MOS transistor has capacitance to the other terminals. It's non-linear and voltage dependent. That is called as CV. Approximated as simple capacitors, simple MOS capacitance models. Gate of the MOS transistor, it is a good capacitor. Capacitance is necessary to attract charges to invert the channel. So high gate capacitance is required to obtain high IDS. The capacitance is Cg, it is equal to C naught X into WL. Most transistors used in logic are of minimum manufacturable length because this results in greater speed and lowers dynamic power consumption, taking this minimum L as constant for a particular process. Cg and C per micron. What is Cg? In the sense, it is equal to C per micron into W. C per micron, it is equal to C naught x L equal to epsilon naught x divided by T naught x into L. In addition to the gate, the source and drain also have the capacitances. These capacitances are not fundamental to operation of the devices but do impact on the circuit performance, and hence it is called as a parasitic capacitors. The source and drain capacitances arise from the PN junctions between the source or drain diffusion and the body, hence are called as a diffusion capacitor, which is CSB and CDB. The depletion region with no free carriers, it forms along the junction. The depletion region acts as an insulator between the conducting P and N type regions, creating a capacitance across the junction. The capacitance of these junctions depends on the area and perimeter of the source and drain diffusion, the depth of diffusion, doping levels, and voltage. Here is a pictorial representation of the different kinds of capacitor which forms in between the three terminals gate, source, body and drain. The capacitor which is formed between the source and body is called as CSB. The capacitor which is formed between the body and drain is called CDB. The capacitor which is formed between gate and drain is called CGD, and the capacitor which is formed between source and gate, it is called CGS, and the capacitance which is formed in between this gate and body is called as CGB. Along with the parameters, what is about the cutoff region, linear region and saturation region can be pictorially mentioned here. For the parameter CGB, that is gate to body capacitor. What happens in the sense, for the cutoff region, it should be less than or equal to C naught, and for the linear region, it is 0, and for the saturation region, it is 0. For the parameter CGS, CGS should be equal to 0 for cutoff region and should be equal to half of the C naught and should be equal to two-thirds of the C naught for the saturation region. For the parameter CGD, it should be equal to 0 for cutoff region and should be equal to half of C naught for the linear region and should be equal to 0 for the saturation region. And for gate capacitance, all these three capacitance has to be sum up, that is CGS plus CGD plus CGB. For the cutoff region, it should be equal to C naught, and for the linear region, it is same, and for the saturation region, it should be two-thirds of C naught. For CGSOL, SOL in the sense, it can be written for the overlap capacitance. It is equal to CGSOL into W. W is the width of the capacitance, and for the overlapping capacitance for the gate to drain overlapping capacitance, it can be given as gate to drain overlapping capacitance into width. Next is a detailed Morse capacitance model. The gate capacitance model has two components, that is the intrinsic capacitance and the overlap capacitance. Intrinsic capacitance is called as CGC, which is kept over the channel, and overlap capacitance is called as CGOL, which is between the source and drain. The intrinsic capacitance was approximated as a simple parallel plate capacitance with capacitance C naught, it is equal to WL C naught X. However, the bottom plate of the capacitor depends on the mode of operation of the transistor. That is, intrinsic capacitor has three components, that is gate to body capacitance, gate to source capacitance, and gate to drain capacitance. And delay calculation can be calculated with the equation of Cg, it is equal to Cgs plus Cgd plus Cgb, that is gate to body capacitance plus gate to source capacitance plus gate to drain capacitance, which is approximately equal to C naught plus 2 Cg naught L into W. The last one is a detailed MOS diffusion capacitance model. PN junction between the source diffusion and body contributes a parasitic capacitance along the depletion region. The capacitance depends on both the area AS and sidewall parameter PS of the source diffusion region. So this is a length, depth, and width of the capacitor. The area can be written as AS, it is equal to W into D. The perimeter can be written as PS, it is equal to 2W plus 2D. The total source parasitic capacitance is CSB, it is equal to ASC into JBS plus PS into C JBS is W. So we have to pictorially mention what is CJBS and CJBS is W. CJBS in the sense it is a capacitance of the junction between the body and the bottom of the source. It has units of capacitance per area. What is CJBSSW in this sense? The capacitance of the junction between the body and the sidewalls of the source. It has a units of capacitance per length. The area junction capacitance term is CJBS. It is equal to CJ into 1 plus VSB divided by psi naught the whole power minus MJ. Built-in potential can be written as, that is psi naught, it is equal to VT into ln of NAND divided by NI square. CD is the junction capacitance with zero bias and is highly process dependent. MJ is a junction gradient coefficient. The sidewall capacitance can be written as CJSW into 1 plus VSB divided by psi SW the whole power minus MJSW. This is the sidewall capacitance which we have given here. And this topic which we are going to see is the non-ideal IV characteristics. So for the non-ideal IV characteristic, we should be familiar with few definition. What is velocity saturation and mobility degradation? What is channel length modulation? What is threshold voltage effect? What are all the body effect? Drain induced barrier lowering, short channel effect, leakage. What about the sharp threshold leakage and leakage is present here? Temperature dependence, geometric dependence, etc. So first of all, let's see the definition for the velocity saturation, mobility degradation, etc. Velocity saturation in the sense at high lateral field strengths, VDS is divided by L. Carrier velocity ceases to increase linearly with field strengths. Mobility degradation in the sense at high vertical field stress, the carriers scatter off the oxide interference more often, lowering their progress. This mobility degradation effect also leads to less current than expected at high VGS. Next is the channel length modulation. So what is channel length modulation? Whenever there is high VDS, that is the increased size of the depletion region around the drain, the effectively shortens the channel. Whenever there is an increase in VDS, the shortens the channel. The threshold voltage effect in the sense you should be clear about what is body effect, what is drain induced barrier lowering, what is short channel effect. Body effect in the sense increasing the potential between the source and body raises the threshold through the body effect. The drain induced barrier lowering in the sense increasing the drain voltage, it lowers the threshold. Short channel effect in the sense increasing the channel length raises the threshold voltage. The leakage, what is a leakage in the channel. Several sources of leakage results in the current flow in nominally off transistors. Even though the transistors is in the off condition, there will be some leakage of the current. So what are the possible ways for the leakage of the current in the sense? It is subthreshold leakage, gate leakage, and junction leakage. Subthreshold leakage is when your gate source voltage is less than Vt. This is a condition when gate source voltage is less than Vt, the current drops off exponentially rather than abruptly becoming zero. When for the gate leakage, the thickness of gate oxide reduces to only a small number of atomic layers. Electrons tunnel through the gate, causing some gate leakage current. The junction leakage in the sense the source and drain diffusions are typically reverse bias diodes and also experience junction leakage into a substrate well. Next one is a temperature dependence. Temperature dependence in the sense it has both the mobility and threshold voltage decreases with the rising temperature. And last one is a geometric dependence. The velocity saturation and mobility degradation in the sense V it is equal to mu into A. Hence current is proportional to the lateral electric field. E lateral it is equal to VDS divided by L between the source and drain. It's only for low electric field. At high fields, this is to be true. Carrier scatter of atoms. Velocity reaches V saturation. This can be written as velocity V it is equal to mu into E lateral divided by 1 plus E lateral divided by E saturation, which is equal to V saturation is mu into E saturation. At high electrical field, a high voltage at the gate of the transistor attracts the carriers to the edge of the channel, causing collisions with the oxide interference that slows the carriers. This is called as a mobility degradation. And the graph is drawn between the E lateral and V saturation. So whenever your E lateral increases, the V saturation increases gradually, which forms the slope which is called as a mu. For an ideal transistor on, the current increases with VDD square. Ideas it is equal to mu into C naught x W divided by L into VGS minus VT the whole square divided by 2, which is equal to beta divided by 2 into VGS minus VT the whole square. Velocity saturated on current increases with VDD. ID is equal to C naught x W into VGS minus VT into Vmax. IDs can be written with the three different criteria, that is a cutoff region, linear region, and saturation region. When VGS is less than VT, it is 0. In the linear region, when VDS is less than VD saturation, ID saturation into VDS divided by VD saturation. For the saturation region, VDS should be greater than VD saturation. It is called as a ID sat. ID sat can be written as PC into beta divided by 2 into VGS minus VT the whole power alpha. VD saturation it is equal to PV into VGS minus VT the whole power alpha divided by 2. And that's all with the first unit about the non-ideal IV effects which we have seen here.